Hi, I'm Timothy Purcella with my Math 1325 class. Today I want to use the general graphing strategy to graph a fourth degree polynomial function. Here's the general graphing strategy that I'll be using. First thing I'll do is find the y-intercepts. If it crosses the y-axis, where does it cross? By setting x equal to 0. That's easy to do, okay? Then I'll find the any x-intercepts if there are any, okay, or if it's not too difficult. In many cases, it's just too difficult to find those things, okay. The third step, I'll use the first derivative test to determine any local extrema. The fourth step, I'll use the second derivative to determine concavity, and the fifth step, I'll determine I will draw the graph, but notice something. I say that just doing steps 1 through 3 by themselves without looking at concavity, you should still get a good picture of the graph. So here's the function I want to look at. Let me tear this page off. Okay, let's see. Here we are. Oh, and for the students that are enrolled in my class right now, this is number 5 in their homework. In my Math 1325 class, this is number 5 in their homework. I want to, first of all, determine the x-intercepts. So, pardon me, I'm going to go through first step, find the y-intercept. I'll set x equal to 0. Setting x to 0, we get y equals 0 to the 4th minus 0, so that's just 0. So the y-intercept, the graph is going to pass through the origin once we draw the graph. When x is 0, y is 0. Second step, we'll find the x-intercepts. We set y equal to 0 there. This is one of those rare problems where finding the x-intercepts aren't too difficult. Set y equal to 0. We can factor out an x squared. That'll leave me an x squared minus 4 in the parentheses. And we can keep factoring. And finally, we want to know when is x squared equal to 0, when is x plus 2 equal to 0, when is x minus 2 equal to 0. That would be when x is 0. Well, we already knew that. When x is 0, y was going to be 0. We already knew that point was going to be on the graph. Here's another one at negative 2, 0. And at positive 2, 0. So the graph is going to pass through. In addition to 0, 0, which we'd already found, the graph is going to pass through negative 2, 0 and positive 2, 0. Third step, we're going to find our local extrema. Let's see, let me push this up some. So we're going to have to differentiate this function on my little list of steps. In my list of steps that I'm using, we're up to the third one. Find local extrema using the first derivative test. So, finding f prime, we get a 4x cubed minus 8x. We ask ourselves, where does that equal 0? And we can factor out, what, a 4x from both of those? Taking out a 4x, we're going to get an x squared minus 2. X squared minus 2 doesn't, that can't be factored using rational numbers anyway. So we say set 4x equal to 0. That gives us x equals 0. So there's my first critical number. Set x squared minus 2 equal to 0. And remember, now I'm going to have to use the square root method. So when we drop the square on the left side, we're going to pick up the positive or negative square root on the right side. So we have 3 critical numbers. Our critical numbers are, let me push this up. So our critical numbers are 0, negative square root of 2, and positive square root of 2. So we're going to draw our number line now. We're going to have to label our critical numbers. Our negative square root of 2 is, of course, to the left. 0, there's positive square root of 2. And we're going to be looking at the sign of f prime. And it might be helpful to remember that the square root of 2, a decimal approximation for that, that's around 1.4. So I'll make a little note there. That's approximately negative 1.4, and that's approximately positive 1.4. It's hard to see that, okay? So we're going to choose a number in each interval and test the inequality. So to the left of negative 1.4, I can choose any number I want to over here. I'll test negative 10. Plugging that into f prime, I'll have a negative cubed is still going to be a negative, so that would be a negative 4,000 plus an 80. That turns out to be negative, so decreasing. Between negative square root of 2 and 0, if I want to use an integer, I only have one option. If I want to use an integer, I better use negative 1. That'll become a negative 4 plus 8. That's positive, so increasing. Between 0 and square root of 2, I'll use a positive 1. That would become a 4 minus 8. Oh, it's changed back to negative, so it's decreasing. And finally, to the right of the square root of 2, we could plug in a positive 10. Let's see, there. We could plug in a positive 10. So we get f prime equals, that would be a 4,000 minus an 80. That's going to be a positive number, so increasing. Hence, we do have a local extreme value, and we have a local minimum occurring at negative square root of 2. We have a local maximum occurring at 0, and what occurs at positive square root of 2? It's decreasing and then increasing, so that's another local minimum. So we have two local minimums. Let me find myself some more scratch paper. Let's see. Okay, so there. Well, I'm just going to have to, here. Okay, I'll just tear this off and come on over to this page now. So, okay. We said that there's a local maximum, there's two local minimums. So we have a local maximum. The local maximum we said occurs when x is 0. Now we're going to have to label this point on the graph. So we may as well determine the y coordinate. When x is 0, what's y? Well, we know that it's 0, 0. That's one of our intercepts. Okay, so we're going to have a local maximum at the origin. Now local minimum, we have to take, first of all, negative square root of 2, plug that in. Then we'll have to take positive square root of 2, plug that in to get our y coordinates. And I think I'm tilted again there. I think that's, okay, well, I guess that's good enough. Plugging in negative square root of 2, you're plugging it into the original function to get the y coordinates, so be careful. Plugging in negative square root of 2, you get y equals, so plugging it in right here, to x to the fourth minus 4x squared. So that's going to be, I'm going to change colors, negative square root of 2 to the fourth minus 4 times negative square root of 2 squared. Well, let's see. The square root of 2 squared is 2, so to the fourth it would be a 4. A negative to even power would become a positive, so we'd have a 4 minus, let's see, this is going to be another 2. Negative squared will become a positive, so we'll have a 4 minus, let's see, 4 minus 8. I'm just forgetting what I'm forgetting what I'm doing here. So 4. I'm getting a y coordinate of negative 4. And I'm going to change colors to plug in. When I plug in the positive square root of 2, I just now realized something. When you plug in a positive square root of 2, regardless, you're going to get the same thing, because whether it's positive or negative, when you raise it to an even power, it's going to become positive. So the thing that distracted me is we're going to have the same number for both of the y coordinates. That's nice. That saved us a little bit of work. Not much, but a little bit. And where's my sequence of steps here? We've just now determined local extrema, so we're now moving on to the next step. Determine concavity using the second derivative. So we have to find, remember, this is the fourth step in our graphing procedure. So now we're going to do the fourth step. Remember, we said f prime was, where's that page? 4x cubed minus 8x. So we're going to find f double prime now. That'll give me a 12x squared minus 8. Okay. And we'll set that equal to 0. And well, there's a common factor of 4. I guess we could set that, we could take out the common factor of 4, but other than that, there's not much we can do. That's a, let's see, a 3x squared minus 2. Setting 3x squared minus 2 equal to 0. We'll have a 3x squared equals 2, so x squared equals 2/3. So x is the positive or negative square root of 2/3. Well, I guess we can say that that's a square root of 2 over the square root of 3. And then we can rationalize above and below by square root of 3. So we're getting two possible x values for inflection points. The square root of 6 all over 3. And I should look back right now, notice something. I just now realize that this problem that I'm doing is a multiple choice problem. So I have it printed out here. Why don't we answer the questions, the information that we already know, okay? We already know some of the answers, so let me see. I'm not going to let you see the graph right now. There, hide that. What did we say all of my papers fell? No, I'm going to go, let me pick them up. Okay, let me do it like this then. What did we say the local extrema were? We have an A, B, or C choice. We said that, where's my work? It's what's covered up here, isn't it? We have a local maximum at 0, 0. We have a local minimum at the negative square root of 2, comma negative 4, and positive square root of 2, comma negative 4. So that would be A, local minimum, local maximum. Let's see the graph. And now the inflection points, okay? We need to show, we're working on the inflection points right now. Let's show that these numbers, we're looking at the sign of f double prime. We have a negative square root of 6 over 3 and a positive square root of 6 over 3. And because of the multiple choice nature of this problem, I probably would not have rationalized this normally, but I glanced over and realized that they've given this as a multiple choice option, and they're given the things in terms of the square root of 6 over 3. So that's how I made my decision to rationalize when I glanced at the multiple choice options and saw that they didn't show a square root of 3 over 2, a square root of 2 over 3. They showed the square root of 6 over 3. So that's why I made that decision to go ahead and rationalize. So we're looking at the sign of f double prime. Let's first of all test a number right there. Testing between negative square root of 6 over 3 and positive square root of 6 over 3. We could obviously one negative, one positive. We could test a 0 and testing f double prime. Here's f double prime. That would be a 0 minus 8. That's negative, so the graph is concave down between those two numbers. Now we need to choose numbers to the right of the square root of 6 over 3 and to the left a negative square root of 6 over 3. Well, the square root of 6, that would be, let's see, it's certainly smaller than, the square root of 6 is certainly smaller than 3. The square root of 9 is 3. So it's something smaller than 3 divided by 3, so that's less than a negative 1. So if we use something like, or you could get a decimal approximation using your calculator, I'm going to use negative 10 and positive 10. So I'm plugging it in up here, plugging it into my second derivative right here. That would give me a 1200 minus 8. F double prime is 1200 minus 8. That's positive, so concave up. And when you plug in positive 10, you would also get that f double prime is positive, so concave upward. So we do have points of inflection. The thing is, I don't generally bother even labeling the points of inflection. I can get nice graphs of polynomial functions without having to resort to plotting the inflection points. The concavity will take care of itself. Looking over here, what do we conclude for concavity? They're going to make us say something. No, that's certainly not the case. There are inflection points, and the inflection points occur at the x-coordinate negative square root of 6 over 3. Notice they've already plugged the numbers in for us. They're saving us some effort. Response B for the inflection point. Now we need to draw our graph. Okay, there are inflection points. I should have summarized this. At negative square root of 6 over 3 and positive square root of 6 over 3. And you'd have to plug those into the original function, and my math labs being nice for us, they're giving us the y coordinates. They should be negative 29ths. So I'll go ahead and write that down, but we really don't need it. I'm not going to label those points when I draw the graph. When I draw the graph, I'm only going to use the intercepts that we found and the local extrema. So where's my local extrema? Here it is. I'm going to draw my XY grid. Let me come up here, move down. I'm drawing my XY grid. And we already know that the graph is going to pass through. The graph is going to pass through the origin. We know that's going to be a point on the graph. Let me one. And I'm going to make, notice I'm making the increments wider on the x-axis than the y-axis. Here, that's 1, 2, 3. Then 1, 2. Okay, there's my XY grid. I need a dark pen. I'm going to label the local maximum at 0, 0. Negative square root of 2. Remember I said that's about a negative 1.4. So left one, where are my negative signs? Right there. So left 1.4, down 4, right out there. Right 1.4. I'm doing this one down now. I'm doing this one, the square root of 2, comma negative 4. So be right out there. And remember when we were drawing our number line, we said the function would be decreasing, then increasing, decreasing, and increasing. So it's decreasing. Now, if your graph misses the point, we all know what to do. You make the point bigger, right? Increasing. I remember that from high school. Decreasing. And there was some other piece of information I failed to take into account. We had found the x-intercepts. They're going to pass through the x-axis at negative 2 and positive 2. That's the problem with doing this with there. That's the problem with doing this with a pen. I can't erase. Pass through the x-axis at negative 2, 0, and positive 2. Ignore that little, hold on, I can fix it. There. Let me get a plain piece of paper. Goodness, I'm running out of paper here, aren't I? Okay, so there. There, I fixed my graph. I'm corrected the error. We have our local minimums. We have our local maximum. It's decreasing, increasing, decreasing, increasing for my final graph. And this is multiple choice now. They want you to choose the correct graph. Well, looking at these 4 options, which one looks like the one that we found? I hope y'all can see this. Looks to me like it's going to be B. Decreasing, increasing, decreasing, increasing. They've shrunk the scale down to what? Units of 5. 1, 2 on the y-axis and units of 1 on the x-axis. Well, I didn't change the scale up that much, so on my graph. But anyway, I hope this helps y'all graphing these polynomial functions. And I think it's Halloween right now as I'm recording this, so Halloween weekend. Oops, there's the wrong piece. Let me cover it over. So I hope y'all have a good weekend. I'm going to take a break and get ready for my next class. Bye.